Okay, as I was just saying, we're going to do some more homework review today to get through the rest of the Chapter 9 assignment that I've given you. However, Chapter 9 assignment will have some questions added onto it next week so we can finish up the section on two-dimensional kinematics, which I think we actually have enough problems for two-dimensional kinematics in the homework, but we will add some homework problems for center of mass, which is kind of a chapter within a chapter. And then we'll do some problems with rocketry, which are good problems for learning about center of mass. But we'll go ahead and we'll save that for next week. We'll do that on Monday probably, maybe a little bit Tuesday. By Wednesday, we hope to have started Chapter 10 so that you have some torque stuff under your belt before you do your lab on Thursday. I think we can get to torque by then. It'll be quick, but we'll get there. All right, so let's see, Chapter 9, we need to do a shift on this side. Make Chapter 9 due next Tuesday, 29th. Don't forget to save. All right. So, let's talk about Chapter 9. Homework. We got through the first 8 yesterday. Is that right? Six, 7. Okay, so in 7, we have a rugby player who's running at 7.25 meters per second, collides head-on with a padded goalpost, experiences a backward momentum. Actually, this is pretty much the same as don't we have one where something hits and then goes backwards? It's essentially the same as this one here, number 2. Except they don't, in number 2, they don't actually calculate the change in momentum, I guess. So I guess it is a bit different. It's not a very difficult problem, number 7. You have some momentum as the player is going downward. The mass of the player times the velocity of the player is the momentum as he's going downward. But remember that momentum has direction. It cares about direction. So the direction of that momentum is down. And if you want to, mathematically, you could call that negative if you want, or positive, doesn't matter. But you need to give it a sign. So once you've calculated it, down, I think in this problem, they're probably assuming that. Well, no, I guess they're not really assuming a direction, so you can assume whatever one you want. So let's say that down is negative. His initial momentum is going to be a negative 112 times 7.25, or 112 times negative 7.25. But anyway, it's going to be a negative number. And then he hits the padded. Oh, sorry, we're not doing down. We're doing sideways. But whatever. Sideways, I keep thinking we were dropping something, but we're not. So sideways, and it ends up being a negative number because we chose that direction to be negative. Then he bounces off of it, and his final velocity is the other direction, and in that other direction, we're going to have a velocity that is positive, and so it's going to have a positive momentum. So the overall change in the momentum is going to be from going negative to going positive, which would be a total positive change in momentum. But change in momentum, we've already learned, is also equal to the impulse, which is what they tell us about here, because they don't tell us his final velocity. They tell us the force that he experiences and the time that he experiences it, which gives us impulse. So if we go to our whiteboard here, so this is our picture here. This is the positive x direction, and his initial velocity is this direction. so it's negative, equals some negative number, whatever it is. And the final velocity is going to be this one, some positive number, whatever it is, we don't know that one. So the change in momentum is going to equal mv final minus mv initial. But it's also equal to, change in momentum is also equal to the force that causes that change times the change in time. And these are the things they give us. But this is the thing they want us to solve. So this equation here is the one we want to use. The force times delta T equals mass times velocity final minus mass times velocity initial. We know the mass, we know the velocity initial, we know the mass, we know the change in time, we know the force, and we're done. But the reason that I talked about that negative positive thing is that on this side of the equation, if you don't get those velocities plugged in with the proper signs, you will not get this problem right. And it doesn't matter which way you choose to be negative, as long as you stick with it. What matters is that you plug them in correctly into the equation so that it gives you the right answer out. And since they're just asking for the speed and not the velocity, then you just take the number that comes out of this equation and take the absolute value and plug it in for your answer. Because they're only asking for the speed. They don't really care what the direction is for this. Does that make sense? All right. So, next. Number 8. So number 8 has a force time graph again. And remember, the force time graph, the change in momentum is equal to the force times the time, so the change in momentum is equal to the area under this curve. And that's also the impulse, and they actually want to know the impulse in this case. They want to know the impulse in these two different time intervals, and so you just calculate the area under the triangle, and then you calculate the area under the rectangle. And then they ask for the change in momentum. Well, the change in momentum is the same as the impulse. So the answers are the same in part B. That's a simple one. The hockey puck. Let's see. So, you have a hockey puck that's starting out with a velocity in the x direction, the positive x direction here. And then a force acts on it, pushing it north for 1.3 seconds. In other words, there is an impulse which causes a change in momentum. So the original momentum is to the right. The final momentum, it's gonna keep its momentum to the right, because the force upward isn't gonna change that at all. But the force upward is gonna give it some momentum upward. So its final momentum is gonna be pointing upward and to the right a little bit. We don't know how much yet. And they want us to calculate the momentums east and the momentums north. Well, the momentum east is the same as it was. We can just calculate that right now. 12 meters per second times 160 grams, and you get 1.92 kilograms meters per second. Remember that to convert that 160 grams into kilograms. But the momentum north is going to be equal to the change in momentum, because originally it has no momentum north, and we give it some momentum by applying this force and creating this impulse. So all we have to do is calculate the impulse. Impulse is equal to force times time, and we have the force. The force in this case is 3 newtons. The time is 1.3 seconds, and it's a constant force, so we don't have to do any integration or anything. But Now we know the northern momentum after that force has been applied by multiplying the 3 newtons times 1.3 seconds, and we get 3.9 kilograms per second of momentum north. So the overall momentum would be the vector, this vector here, 1.92 I hat, plus 3.9 j hat, if I hat is east and j hat is north. Right? They don't ask for that, but that's what it would be in vector notation. So in number 10, you have a ball that's dropped and then hits the floor and rebounds. If the ball hits the floor at the speed of this and then it rebounds with the speed of this, it's contact flow forward 2.7. They want to calculate the change in momentum. Let's see. Magnitude of the change in the ball's momentum. And then it says the change in the magnitude of the ball's momentum. Those two things are the same, aren't they? I'm not understanding why they have two different. Oh no, oh sorry. No, that's actually not. Magnitude of the change in the ball's momentum. No, I think that's actually written wrong in part B. Oh, no, 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 I see what they're saying. I see what they're saying. Okay. So what is the difference between saying the magnitude of the change in ball's momentum or the change in the magnitude of the ball's momentum? These are the same exact words, just a little rearranged, right? What this means is, for part A, or the first part there, you have the ball coming down like this, and then the ball bouncing up again with this new velocity afterwards, right? The velocity before in this problem is bigger than the velocity after. Velocity initial is greater than the velocity, the magnitude, if you just take the magnitudes. So the magnitude of velocity initial is greater than the final velocity. And that's because there was some energy loss in the transfer. And they want to know what is the change in momentum. The change in momentum, of course, is where you use the signs and calculate the change in momentum. You use the correct signs, calculate the change in momentum, mv final minus mv initial, using the correct signs. So this one could very well end up positive or negative. But then when you're done, take the absolute value of it. But then what is the change in the magnitudes? So this is part A, which is the magnitude of the change. The change in the magnitudes is you calculate mv initial, or mv final, and take its magnitude. And then you subtract from it the magnitude of mv initial. And you say, what's going to be the difference? What's the difference between these two? Let's see, did I say that right? Let me check just to make sure I said that right according to the problem here. Yeah, the magnitude of the change and the change in the magnitudes. Yeah. And then they say let negative values indicate a decrease in magnitude. So, in other words, this one is always going to end up being positive. This one would be positive if the final is greater than the initial. It'll be negative if the initial is greater than the final. And since we already know the initial is greater than the final, we know this one's going to end up negative because it's just assigned that way. So anyway, that's the difference between those two, and that's all you're doing. This is the math of the first problem part. It's the math of the second part. And done. And it says the average force the floor exerts on the ball during their interaction. So the average force is the force from the impulse, which will be equal to part A times the time. I'm sorry, it'll be equal to point. It'll be equal to part A divided by the time, not times the time. Because force times time equals impulse, or force times time equals change in momentum, so change in momentum divided by time is force. So you take your change in momentum from part A and you divide by the time, and you put that into part C. All right. Volleyball. I was just playing volleyball last night. That's why I'm so tired. One of the reasons I'm so tired. Goodness. Really weird thing happened to me last night. I got home late from volleyball. It was like 11 something. And I was eating a salad because I was a little hungry and I was watching a movie while I was eating. And then the phone rang. And I look up and it's like midnight. And the phone is ringing. What the heck is going on? And I'm a little bit sleepy and kind of like not there. I'm not all there. I was kind of falling asleep because I just finished eating and I was getting all groggy. So I answer the phone and there's this like young girl's voice on the other side and she's like super hyper. And I'm like, hello, who is this? This is Jordan. And I'm like, Jordan, who do I know that's got a name Jordan? And I'm like listing through all these people that I think are named Jordan, but because I'm tired, I'm sure none of them are named Jordan. And I can see on the caller ID, like the full name is Jordan Leal. She's like, we're really freaked out and we don't know where to go to feel safe. And I'm like, who is this person? And I said, what do you want me to do? Well, can we come over to your house? And I'm like, who is this? I'm like, do you know where my house is? Yes, I know where your house is. I said, okay, come on over. I'll get my wife up. I figure if they do know where my house is, it's probably somebody we know. And then on my way upstairs to wake up my wife, I realized who it was. I'm like, oh, it's a friend of ours from church who lives around the corner, and they've got a couple of teenage daughters that go to school with our teenage daughter. You know, and I'm like, I don't really know what happened, but I wake up my wife. I'm like, I don't really know what happened, but these kids are freaked out. Maybe their parents aren't home or something. So they come over, and there's 4 of them. There's the daughters who were twins, and then their friends. And you guys heard of this murder that happened like here a long time ago? People talk about it a lot here. But this murder where this mom killed a bunch of people and her family and all this crazy stuff. There's a book. Yeah. Well, there was a book written about this one, and it was pretty like crazy, like make a movie out of it crazy.
The Hancock story?
What's that?
The Hancock story?
Yeah, I think that's it. Well, anyway, this family has lived here forever, and they knew them, and like were close friends with them, and close friends with this woman, and they knew where the house was and all these things. Their house, that family home was, and that's kind of their thing to go and like visit this house during the Halloween time and get all freaked out. But they were visiting it in the middle of the night, and apparently somebody had taken up residence there, like just some squatter, you know, kind of taking residence in this house. And they're visiting this house in the middle of the night, and they're like, "What the heck? Why are you in my house?" They're having like this sleepover party, and they're freaking out, and their parents aren't around, and I'm like, "Oh goodness, why do I have to deal with this teenage drama in the middle of the night? I'm so tired." So like at 1:30 last night, they finally left. I'm like, "Oh, you gotta be kidding me." So anyway, Yeah, volleyball. Sorry, my brain's totally shot. I'm so tired. Okay. Spiking the ball changes the velocity from 4.6 meters to negative 23 points. Holy crap. I want to recruit this volleyball player. I don't think there's a professional woman volleyball player that can hit that hard on the planet today. There are a couple of men that can, but not many women. I don't think any women can hit that hard. But it's pretty amazing. So, um, so this is a change. What is the change? You take the final, which is minus 23.7, minus the initial 4.6, and you're going to get a negative 28.3, right? So that's the change in velocity times the mass of the ball equals the force times the times the time, which is the impulse which they give you. So you just take this change in velocity, multiply it by m, and then set it equal to the impulse they give you, and then solve for m by dividing by the change in velocity on both sides. And you'll get the mass of the ball, 2.259 kilograms. That's about right. Half a pound. Yeah, it's about the mass of the volleyball. They actually had to start making the ball heavier in volleyball because there were some guys that were hitting the ball at 70, 80 miles an hour, and it was just hurting people. Like, people were in danger. There was one guy, Clay Stanley, who hit for the United States, who hit the ball at a record speed of 140 kilometers per hour, which is so fast, like 90 miles an hour or something like that, 80 something miles an hour. And he hit a guy in the face and knocked him flat. Just knocked him on his back. And the guy's like trying to get up, and he's like wobbling and shaking his head. And concussion city. Anyway. All right. So in number 12 here, we're going to calculate three things from this graph. We're going to figure out three things from this graph. They tell us the mass of the object, and they tell us that it's acted on by a force in the x direction. That is shown in this graph. So of course the area under the curve is going to be what? What will the area under the curve be equal to in a force time graph? It'll be equal to impulse, and also equal to what? Impulse is also equal to change in momentum, right? So if you can calculate the impulse, you can calculate the change in momentum. So impulse is the first one. You're just going to calculate the area under that curve, and you're going to be done. The final velocity of the particle, if it's initially at rest. Well, remember that impulse is always equal to the change in momentum. So you can use that equation. We go back here. Impulse, which is force times delta t, which is your impulse, is also equal to change in momentum. So whatever your force times delta t is, which in this case is our area, is equal to mass velocity final minus mass times velocity initial. And in this case, since it starts at zero velocity, it's just this equation right here. The area equals the mass times velocity. So you divide your area by the mass and you get your velocity. You're good to go. And the final velocity of the particle if it's initially moving at negative 1.8. Well, you use the same equation. You come back to this equation again. But instead of plugging in 0 for initial velocity, you plug in the initial velocity that's a negative value, and you go ahead and calculate again. Calculate the final velocity in that In number 13, you have a bullet that is fired from a rifle. You know, you're given the mass of the bullet, you're given the weight of the rifle. So you want to probably take the weight of the rifle and calculate its mass by dividing by 9.8 to start. And then they want to determine the recoil speed of the rifle. This is a very simple problem. Both parts A and B use the same equation but with different numbers in it. And it looks like this. You have your rifle. This is going to be a beautiful rifle. Right? And you have your bullet. While the bullet's in the gun, before you fire it, the momentum of the gun and the bullet system is equal to 0. After you fire the gun, momentum initial. After you fire the gun, the momentum of the bullet in the gun is also equal to 0. Before you fire it, it's the mass of the bullet plus the mass of the gun times the velocity of the bullet and the gun combined, which is 0. Right? That's why it's 0 at the beginning. The reason it's 0 at the end is because the bullet and the rifle are going on opposite directions with equal and opposite momentums. So here's your rifle at the end, and it's going off in the left-hand direction velocity, with a little velocity, but the bullet on the right side is going off into the right-hand direction with a huge velocity. The bullet has a small mass, the rifle has a big mass, and that's what accounts for it. So in the end, you know that mass of the gun times the velocity of the gun plus mass of the bullet times the velocity of the bullet has to equal 0. And you plug in the things you know, solve for the things you don't, and you're good to go. So that is number 13. In number 14, you have to explain why that's true. I'll leave that for you to do. You have to pick the best explanation for why that's true. So in this one we have a momentum time graph. This is not a force time graph. This is a momentum time graph. So this tells you the momentum of this system. And you have two cars traveling across a horizontal surface in the same direction, and this car 1 catches up to car 2, and they stick together. It's totally inelastic, but the momentum changes. Knowing the friction in the wheels of the cars are going to be treated as massless. I actually have a tutorial for this one, so I'm going to let you go ahead and do the tutorial and kind of figure out that on your own. It's not terribly difficult, but I'll let you do that. Here we talked about this experiment, I think, didn't we? Can't remember, but I think we did. This is a famous experiment that that led to the discovery of the nucleus of the atom, and it just led to the current model of the atom that we use now. Ernst Rutherford, who was a physicist in New Zealand, he's actually, is he in this picture? No, that's J.J. But Ernst Rutherford was a physicist in New Zealand who was trying to discover what atoms had at their core. At that time, they had what they call the plum pudding model, which suggested that atoms were made of this kind of squishy stuff that had chunks of negatively charged particles in them. Because we knew about the existence of electrons, but Rutherford decided to use radioactive particles coming out of radium and shoot these particles at gold nucleuses. And what he discovered is that it behaved exactly like the plum pudding model predicted, except in one case. And it was actually a student that discovered the one case. And that one case is that every 1,000 particles that went through, one came almost straight back. And so the only real conclusion is that it's mostly empty space except for one really massive thing in the middle, which is positively charged. So anyway, that's a conservation of momentum problem there in 2 dimensions, which we'll get to next week. Talk about that next week. Any questions before we're done, Colleen?
Not that I can think of at the moment.
What's that?
Not that I can think of at the moment, but are you going to be removing any more problems?
I don't think so. I think we'll be leaving the rest of these in. Yeah, we'll leave the rest of these in for sure.
Okay, because if you were going to try to remove more problems, I would have stopped working because some of the ones that you removed before were ones I had already done. So
Well, you get extra knowledge from that, right?
it's only like 3 points. It's not gonna. Oh, speaking of points, the chapter 7 thing for that one.
Okay, I'll do it right now.
Thank you.
We'll add a point to everybody's chapter 7 right now. I'll go do it in my office though, so that I'm not doing it. But I can do it. All right, I got to end my recording. But